This lecture, we're going to cover glaciers and glaciation. So first, what is a glacier? A glacier is a thick ice mass that forms over hundreds or thousands of years. It originates on land, and it accumulates from the accumulation, compaction, and recrystallization of snow. There's two types of glaciers: Alpine glaciers, which are found in high altitude or mountainous valleys, and ice sheets, which are large sheets that cover continents. So ice on water is known as sea ice. It's not a glacier. Only ice on land is known as a glacier. So alpine glaciers are glaciers located in the valleys of high altitude mountains. And each glacier is a stream of ice that flows very slowly down the valley. And there's thousands of these glaciers that exist. Where ice sheets are these enormous masses of ice that cover large areas. Unlike alpine glaciers that flow down the valley, ice sheets flow in all directions that move away from where the snow is accumulating, the accumulation centers. There's only two ice sheets that exist today, the Greenland ice sheet and the Antarctic ice sheet. So how a glacier forms is there's some location, either it's high altitude, or in case of an alpine glacier, or it's high latitude near the poles, in case of an ice sheet, where it's cool enough that all the snow that falls in the winter doesn't melt in the following summer. And as a result, year after year, there's a net accumulation of snow. And that is known as the zone of accumulation. So here's the snow line. The snow line is the point of a mountain, say, where there's always snow, right? The snow doesn't melt. So year after year, snow accumulates. As that snow accumulates, it compacts and recrystallizes into ice. And this region is called the zone of accumulation. This is where the glacier forms. And then the glacier begins to flow. It's always flowing. It flows under its own weight due to gravity. It flows down valley or away from where the snow is accumulating, in case of the ice sheet. And down here is the zone of wastage. This is where all the snow that falls in winter melts. Not only does that snow melt, but some of the ice either is melted or it breaks off. And so this is called the zone of wastage. Now, if the rate of addition of ice at the zone of accumulation is equal to the rate of subtraction of ice at the zone of wastage, then the glacier is stationary. It doesn't move. However, if the climate cools and the rate of accumulation is greater than the rate of wastage, then the glacier advances, the front of it advances. Same thing is true with an ice sheet. If the climate warms and the zone of wastage, the rate of wastage exceeds the rate of accumulation, then the glacier retreats. So how a glacier moves. Ice moves at the slowest rate at the bottom because of friction. The rock really has to, ice literally has to slide along the rock, so it's friction. But as you move up, you see that the ice actually flows faster. And so the ice deforms plastically. And so it's a solid, but it can deform slowly on long time scales. It's similar to what we talked about, the mantle, the rock in the mantle, though it's not that stiff. It's a little bit more plastic than the rock in the mantle. And so the ice at the top of the glacier is actually flowing faster than the ice at the bottom of the glacier. So if you drilled a hole in the glacier, put a metal rod in it, and came back sometime later, you'd see that metal rod being bent as so. So glaciers, they contribute to a lot of erosion. And glaciers can have a significant formative effect on a landscape. So here's a landscape pre-glaciation. Okay, so here is a landscape pre-glaciation. So you can see they just have these deep V-shaped valleys from the stream channels. But when it's glaciated, what happens is the glaciers now form in all these stream channels, these stream valleys. And they transformed the V-shaped valleys into these broad, deep U-shaped valleys. They carved the valleys wider and deeper. They form what are known as glacial troughs. So you have the main glacier flowing through the main stream of the main valley, and then all these tributary glaciers flowing into it. So the head of a glacier, it forms this semicircular region called a cirque. See the cirque right here. And the ridge between two glacial valleys, because the valleys are carved steeper, it creates a sharp ridge, known as an arete. And the peaks of mountains, because the mountains are carved steeper, they form more jagged peaks. They're called glacial horns. Then obviously you have the main glacial trough, and where the smaller tributary valleys dump into the main glacier, whenever the glacier is gone, it forms these hanging valleys, like you can see here. So you can see how glaciation has shaped this landscape from here to here. So here you can see an example of a glacial trough, this broad U-shaped valley. And here's a glacial horn. This is actually a very famous horn. This is the Matterhorn in Switzerland. See how it's a very steep mountain. So it's carved by, steep by glaciation. So not only do glaciers shape landscapes by removing material through erosion, but they deposit that sediment somewhere else, and that shapes that landscape. So glaciers, they transport sediment in these linear features called moraines. There are several types of moraines. There's lateral moraines. Those are the sediment that's drug along the side of a glacier. And so each glacier has two lateral moraines on the edges of it. Where two glaciers flow together, their lateral moraines come together to form what's known as a medial moraine. So you can see in this illustration here, the lateral moraine of this glacier and the lateral moraine of this glacier, they flow together to form this medial moraine, which is now sediment that's being transported within the glacier. So each time you see a medial moraine, it's formed by two glaciers flowing together. So you can see how a glacier flows into the main glacier up here. So this forms a medial moraine. This glacier is flowing into this glacier, so that forms a medial moraine. And so every time you see these medial moraines, it forms from glaciers that flow together. So each of these were their own glaciers that have flowed into the main valley. And what you can't see here are end moraines. Those are linear deposits of sediment that are sediment features that are in the front of the glacier. So what glaciers leave behind, they also leave behind these kettle ponds. Kettle ponds are actually very interesting how they form. So as a glacier is retreating, right, so this is the glacier. This is an ice sheet throughout Alpine Glacier. As it's retreating, chunks of ice will break off and be left behind. Now all the meltwater flowing underneath the glacier transferring a bunch of sediment. That sediment is deposited. It's deposited around that chunk of ice. That whenever that chunk of ice finally melts, these layers of sediment have been deposited, but there's this hole where that chunk of ice used to be. Then it fills in with water, forming these kettle ponds. So Rhode Island has a lot of different kettle ponds. As you can see, in this region, they're a result of the last ice age, glaciation. But the kettle ponds of New England don't compare to the kettle ponds of the Midwest. So for example, Minnesota, kind of 10,000 lakes, or where Land O'Lakes butter comes from, you can see where it gets its name. If you zoom in, there's all these little tiny lakes. These are all the result of kettle ponds. You can imagine as the ice sheet was retreating in the last ice age, these are all chunks of ice that are left behind, and the sediment was deposited around, and as they melted away, water filled in those holes. You can see all these little tiny lakes. And so we're also into Wisconsin, as well, in northern Wisconsin as well. So it's funny. I have relatives that live in Wisconsin, and a couple of years ago they bought a lake house in northern Wisconsin. And so I said, "Oh, so you're telling me you bought a house in northern Wisconsin?" Because it's kind of hard to buy a house in northern Wisconsin that's not on a lake, right? Because there's so many different lakes. But these are all, features that are a result of the ice sheet, the retreating ice sheet. And these outwash plains, which is the sediment that's deposited around the chunks of ice that result in the formation of kettle ponds. There are the plains in front of glaciers where all the sediment is deposited. So it's a very fine sediment because, as I said, the meltwater, it flows underneath the glacier, and the space between the glacier and the bedrock is so small, only fine sediment can be transported. It's all deposited up front of sediment. So sand and mud forms these outwash plains. Then you have things like eskers, which you have these streams that are flowing underneath glaciers, and they deposit sediment along the bed of the stream. The stream is contained by the walls of ice on each side, and it deposits sediment. And as the ice retreats, that sediment that was deposited there, it remains, and so it looks like it's just this pile of sediment, but that was a flowing water that was bounded on both sides by the ice as it flowed along the bottom of the glacier. Also, where water falls down, water over the top of the glacier falls down through a hole, and then it flows, it creates these drumlin fields as it deposits sediment. Then you have these end moraines, which as the glacier moves forward, it drops sediment that was pushing in front of it, these end moraines. And the one that marks the maximal advance of the glacier, that is the terminal moraine. And then as the glacier retreats, as the climate warms, sometimes the climate cools for a little bit, and the glacier re-advances and deposits another end moraine. And then once the glacier begins to retreat again, when the climate begins to warm. So there's always one terminal moraine, and then there could be several recessional moraines behind it. So southern New England and New York has a lot of end moraines. They actually are that form the backbone of a lot of features we know. So Nantucket, Martha's Vineyard, Block Island, and the South Fork of Long Island are all a terminal moraine from the Laurentide ice sheet, which was the ice sheet that covered North America during the last ice age. Then as the ice retreated, it formed a recessional moraine. It formed the North Fork of Long Island. It runs up through southern Rhode Island, down here, these islands, and then it forms the backbone of the Cape. So you can actually see this moraine running through southern Rhode Island. So you can see the moraine running through here in the North Fork of Long Island. And Fisher Island is part of that same moraine. And you can see this material right here. This is the glacial moraine. This is the end moraine. It's a recessional moraine, right? And it runs up here through southern Rhode Island. It's called the Charlestown Moraine. And Route 1A is right on the southern edge of the moraine, Route 1. You can see the moraine goes up through here, all through southern Rhode Island. And then it's submerged there. And you can see this is the same moraine up here. It forms these islands. It comes up here and it forms the backbone of the Cape. So all these features form from these moraines, and then they've been shaped by marine processes like the waves depositing more sediment on them, adding sediment onto them, forming these features like the islands and the Cape. So you can see that's right about where the maximal advance of the Laurentide ice sheet was. Right, so it's southern New England, right on the coast, and Long Island of New York. And during the Ice Age, sea levels were lower because the water that was in the glaciers came from the ocean. So whenever that snowfall accumulated on land, that snowfall came from water evaporating from the ocean. So as all that water, 70 million cubic kilometers of snow and ice covered the continents, it came from the ocean, so sea levels were lower, 130 meters lower than they are today. So this was the coastline in the peak last ice age. Here is the present day coastline. This is the light green. And the dark green would be where the coastline would be if all of the glacial ice on Earth melted today. And whenever the glaciers melt, the meltwater flows into the ocean, so sea levels rise. That's why sea levels have been rising since the peak of the last ice age, about 20,000 years ago. And you can see that during the last ice age, sea level was low enough that the land bridge existed between Asia and North America. This is all above sea level, which allowed species of mammals, including humans, to migrate from Asia to North America and North America to Asia. So where we live today, this was well above sea level during the last ice age. The coastline was here at the edge of the North American continent. But as the ice sheet flowed over North America, it flowed into river valleys and carved them wider and deeper. And it did that for river valleys, such as the Providence River, Seekonk River, and so forth. It carved them wider and deeper. And whenever this glaciers retreated and sea levels rose, those river valleys that are carved wider and deeper, they flooded and formed the Narragansett Bay. And so the Narragansett Bay is a feature of the last ice age. So a lot of the geography of southern New England and of southern New York are very, very recent, and they're a phenomenon. They're produced by the recent ice age, and they're 20,000 years old or younger. So it's one of the few features on Earth that is actually younger than our species, which is pretty cool. So that concludes our lecture on glaciation.